Hi everyone, welcome back to Dave's Math channel. I'm your host David Tear. Today I'm going to finally give a proof of the fundamental theorem of calculus. This is the theorem which is probably the most important theorem, important result in calculus. It says that differentiation and integration are opposites. And this will save us a lot of work in the future because we'll no longer have to do numerical integration, at least for some reasonably simple functions to integrate. We'll be able to integrate a lot of important functions just using this theorem. And there's two forms of the theorem. They're shown on this slide. Here's a more detailed description. I already went over this a couple weeks ago, but I'm going to do it again because this is very important, and we're going to prove this result today. So I wrote these as two theorems, FTC1 and FTC2. FTC1 basically says that the derivative of an integral gives you back the original function. And then FTC2 says the opposite. If you integrate a derivative, you get back the original function, or you get the difference from the endpoints. So anyway, we're going to prove both of these results. And let's start with the first one. So here's sort of a pictorial proof of the first FTC1. So we're defining this function a of x. Here they call it a of x, capital A of x. That's just the area, because an integral, definite integral, like I said earlier, is an area under a curve. So we're taking the area under the curve of little f of x, where x goes from little a to little x. And little x you're supposed to think of as a variable, but little a, the lower limit, is a constant. And we're varying this. So we want to know how much it changes when we want to know the difference between a of x plus h, where h is some small number, minus a of x. And of course, when we take the derivative, we have to divide the whole thing by h and take the limit as h goes to 0. Well, let's look at the difference first. So the difference in those areas, a of x plus h minus a of x, is just the area of this this narrow red region. Well, this narrow red region is approximately a rectangle. I think you guys can see that. And you know how to calculate the area of a rectangle. It's just base times height. And the base in this case is little h, and the height is approximately little f of x. There's an error term here, which is very small, and it gets smaller as h goes to 0. It even gets smaller relative to the area of the wedge. So that's sort of a visual, and then so that what that means is that a of x plus h minus a of x is going to be equal to a little f of x times h approximately. And of course, if you want to calculate the derivative of a of x, you have to divide everything by h, so that's going to give f of x. So that's how you get the FTC1. But here's a more detailed proof of the theorem. So this is just using the definition. Here they changed the name of the variables a little bit. They're using capital F instead of capital A. So we're taking the derivative of capital F of x, which is just the area, or if you like, the definite integral, as a function of x, and we'd use the definition of the derivative. It's just equal to capital F of x plus h minus capital F of x, all divided by h. So we just use the definition of capital of f of x. That gives us the integral from, here they're using the variable t, which I actually think is a better convention. So the first term is going to be the definite integral of little f of t, t going from a to x plus h. And then the second term is the same integral, but going from a to x. We take the difference, and that's just equal to the definite integral from x to x plus h of little f of t, and we're dividing that by h. And technically, this integral, on the second line, is equal to little f of x times h plus an error term. The error term turns out to be big O of h squared. I think I introduced the big O notation a couple weeks ago. It just means that it's in the limit as which h goes to 0 is proportional to h squared, just some constant times h squared. But we're letting h go to 0. We're dividing the whole thing by h. That's going to give us a little big O of h. But since h is going to 0, this term vanishes, and we're just left with f of x. So that's the proof. Now you've seen the proof of the FTC1, which is the first version of the fundamental theorem of calculus. And the second version is very easy to get from the first. So here's the proof of the second version. So now what we're going to do is we're going to find this function capital G of x to be the integral from a to x of little f of t dt. And we want to prove that capital G of x is an antiderivative. Well, let's see how this works. So let's say capital F. Now we're going to find a different function, a different antiderivative. Capital F of x, we're just going to let be some antiderivative of little f of t. That just means some function whose derivative, f prime of x, is equal to little f of x. So let's see what happens when we do this. Well, the way this works is since capital F of x is an antiderivative, we know that at least up to a constant, it's equal to, how does this work? I forget how this works. Yeah. Well, we already proved that one version of the fundamental theorem of calculus, right? We proved that the derivative of g, the way we define capital G, we know that g prime is equal to little f. So if g prime is little f, and we're defining some antiderivative capital F is also an antiderivative, we know that all antiderivatives have to be equal up to a constant because the difference is equal to a constant if we take the derivative. We know is equal to 0, and we know that the only kind of functions whose derivative is equal to 0 are constants. So that completes the proof. We just proved that the integral of from a to b of little f of x dx is equal to g of b which is equal to f of b minus f of a. That's the second form of the fundamental theorem of calculus. It's really just a corollary of the first form. First form is the harder one to prove. But anyway, that completes the proof of the fundamental theorem of calculus. And thank you for watching. Long live math, and I'll see you guys next time. Bye.